So first of all, thank you Professor Corwes and Professor Husing for the opportunity to present my master's thesis at IGMR Group. My supervisor Stefan Octavian Bezrukov and Till Rickert for their continuous support and guidance throughout the whole master's thesis duration, and all of you members of the IGMR Group for attending my master's thesis defense today. The topic for my master's thesis is fabric manipulation for grasping using deep reinforcement learning to expose a flat graspable seam in simulation. I'll begin by first introducing the problem and then defining the methodology used in this thesis work, and then laying out the results and then summarizing the whole thesis. So in introduction, I'll first present the motivation behind the work and then define the problem and lay out the objectives. In methodology, basically I'll start with first selection of relevant tools and then implementation of all of these selected tools, which would be followed by design of experiments, which is also the primary contribution of this thesis work. After this, I'll present the results or evaluation of the designed experiments, and this will be followed by future scope challenges encountered during this work and a conclusion of the overall thesis presentation. We often take for granted our ability to perform mundane tasks like opening a bottle, chopping vegetables, folding clothes, and washing dishes. Such mundane everyday tasks that we humans perform very easily on an everyday basis are actually incredibly challenging for the robots to perform. How do we make sense of this complexity? It is often said that if you truly want to understand something, then the best way is to demonstrate, to build it. And to understand the complexity of human manipulation, the best way to do is to make a robot learn the manipulation task to perform manipulation of everyday objects. This falls under the category of robot manipulation. Robot manipulation is defined as the way the robots interact with surrounding objects to achieve a desired result. And manipulation of these everyday objects like plastic bottles, clothes, rubber toys, fruits and vegetables, and sponges fall under the category of deformable object manipulation. Deformable object manipulation is particularly challenging because of two major reasons. One is unclear state representation and the other is complex nonlinear dynamics of these objects. I'll begin by first defining the problem. To define the problem, I have to lay a context of the problem. So at Suits, the primary problem is that of fabric manipulation for grasping, and the primary challenge is that of handling of towels in order to feed it to a folding machine for further processing. This is done by means of several steps which range from bin picking, that is picking a towel one after another from a heap of towels placed inside a bin, to pre-manipulation, which is exposing a flat seam on the picked up towel and then grasping the towel and then flattening the towel. Pre-manipulation is essentially one of the major steps because the rest of the steps depend on this process. Currently, the pre-manipulation process is done by using a mechanical arrangement in order to obtain a flat graspable seam. A flat graspable seam can be defined as a seam that is unwrinkled, not curved at all, without any overlap, lying fully flat on surface, and the adjacent area of the seam is also fully flat. The problem with the way pre-manipulation is done currently in this particular pipeline is that it's done using a mechanical arrangement which is unreliable, as it requires specific conditions like friction, mechanical contact, etc. to be very strictly met, and as a result a flat seam is not always obtained. This is where deep reinforcement learning comes into picture, and a deep reinforcement learning based approach is explored as part of this thesis to solve this pre-manipulation or flat seam exposure problem. A reinforcement learning problem is defined such that an agent performs an action which modifies the environment, in this case a cloth environment, and observations are obtained, and then the rewards are obtained based on the observations. This process is continuously repeated till a goal state is achieved. So there are a few components of this problem that I would be defining in the coming slides. So these components are, first of all, for the agent, it's defining of the reinforcement learning algorithm and reinforcement learning framework. For the cloth environment, it's the simulation platform, and for rewards, observations, and actions, it's defining the reinforcement learning environment toolkit. Starting with the methodology, which begins by selection of all of the tools that we defined. The objectives can be laid down as after selection of tools, implementation of these, preparing an implementation using the selected tools, and then this is followed by design and evaluation of experiments. This is followed by redesign of experiments for a real robot, performing domain randomization and transfer learning to an actual robot. So there are three major components of this. One is tool selection, implementation, experimentation, and these fall under methodology, and they will be covered as part of this work, and a future scope which is not covered as part of this thesis work. So all of these tools are selected, and for simulation platform, Mojoko is chosen as a major as the primary simulation platform because of the following reasons. First, it has high simulation speed and stability. Second is because of its ease of model creation and accuracy, and the third is because of its good online support. And for reinforcement learning environment toolkit, DeepMind Control Suite package is used for similar reasons, but also because of its good support for Mojoko physics, Mojoko physics engine. So basically, both of these tools are compatible with one another, and the selection of these tools also requires that all of the tools are compatible with each other. So the reinforcement learning algorithm that is used is a soft actor critic, which is one of the actor critic algorithms that is used for continuous action spaces, like in the case of fabrics, like in our case, and it is more stable and data efficient than the existing actor critic approaches. For a reinforcement learning framework, Stable Baselines 3 is used because of its ease of utility, reliability, and good documentation. And moving to the implementation, it involves installation and setup of all of the selected tools, then setting up the project, which includes Mojoko inside a DeepMind Control Suite environment, and the DeepMind Control Suite environment is then converted to OpenAI Gym because Stable Baselines 3 only supports OpenAI Gym environments, and the Stable Baselines 3 framework now has a set of implementations of different algorithms, including soft actor critic, which is used in this work. This is followed by testing of the implementation and making sure the implementation works by testing it on an image-based experiment which has image-based observations and rewards. Moving to design of experiments, the cloth is first represented in a Mojoko setting. The cloth is represented by means of a grid structure such that the primary unit is a capsule, and each of these capsules are actually connected by universal joints of 2 degrees of freedom each. The cloth is placed inside on top of a platform, and the coordinate system is defined with respect to the platform such that the center point of the platform represents the main reference frame, and when the cloth falls fully flat on the platform, then the point G24 falls on the center point of the platform, and all of these points are labeled with this terminology such that the corner points are labeled as G00, G08, G80 and G88 for a 9x9 cloth, and so on. Each of these points are separated by a distance of 0.03 meters, and all units are expressed in meters in this diagram. To make the process of experiment design easier, I categorize the experiments into several categories in order to estimate the number of training steps required for convergence and to also verify a pre-manipulation concept. The experiments are primarily categorized into three categories: preliminary experiments, test experiments, and pre-manipulation experiments. For preliminary experiments, a cloth is placed in a fixed position, in a fully flattened fixed position, and the goal state is to move one or more points to fixed positions. For test experiments, the cloth is randomly initialized and it's in a wrinkled position, and one or more points have to move to fixed positions. For pre-manipulation experiments, which are the full-fledged experiments, the goal is to obtain a fully flat seam from a random initialization of the cloth. Likewise, the cloth types have also been categorized into three categories, namely minimal, intermediate, and full. The minimal type cloth moves one or two points to fixed position, and the initialization depends on the experiment category. The intermediate type experiment moves 3 seam points to fixed positions, and the full type cloth moves 5 seam points to the fixed position. The primary result that is directly translatable to the real world setting is that of experiment 5.3.F3.1, because it uses the full-fledged cloth, the full size cloth. Apart from that, rewards are also categorized into three categories, namely distance-based approach, projection-based approach, and slope-based approach, which I'll cover in the coming slides. So, as I mentioned, the cloth initialization is of two types. One is fixed and the other is random. So, a fixed type cloth is fully flattened on the platform, whereas a random type cloth is randomly oriented, and it could be anywhere on the platform, and the points on the cloth could be randomly oriented. The cloth state can consist of a single, just the seam points and its neighboring points, and the full size cloth. The action is performed only on the corners in this study, and it consists either of two-dimensional action in the X and Y direction, so either pulling or pushing it in the X and Y in the XY plane, or it could also be three-dimensional, and in which case we also select one of the four corners. In either case, the action range is from minus 0.05 to 0.05 in each of X, Y, and Z direction. The primary purpose of reward is to flatten the piece of cloth fully, and a distance-based approach means that for the case of moving one or more points to fixed positions, the larger the distance from the fixed goal position, the higher the punishment would be, and the closer it is to the goal position, the higher reward would be. And this is how the agent learns to move the cloth to fixed position. For a projection-based approach, the cloth points which are randomly positioned are projected onto an ideal line, and the distance of each of these points is calculated, and based on the distance a reward or punishment is obtained. For a slope-based approach, just the slopes of all of the lines joining the points is compared, and if the slopes of all of those points are to a certain degree same, then that means that a flat seam is obtained. So all of these concepts are just different ways of obtaining the flat graspable seam. So I'll take just the pre-manipulation experiments of each of these cloth categories and explain how the experiment design process looks like. So for a pre-manipulation experiment for a minimal type cloth, which is of 3 by 3 grid size, 2 points are essentially pushed towards the ground in order to flatten it, such that distances in the Z direction are minimized. So the reward is essentially proportional to the negative value of the Z component of G00 and G01 labeled in this figure. For a pre-manipulation experiment for an intermediate type cloth, which is of 6 by 6 grid size, a more complex reward-based approach is used that is based on slope that we saw in the previous slide. So here the difference in the slopes is calculated, and the reward is proportional to the difference in the slopes, but additional rewards are given. for the seam points on the ground. So if the seam points and its neighboring points are on the ground, then the agent is rewarded highly. And if no cloth portion is in the seam region, so a seam region is defined such that no cloth portion should be around that seam region. This is to prevent overlap within the cloth. Likewise, for a full-fledged size cloth, the slope-based approach is used with the intermediate type cloth is directly translated, which means that the approach is same except that we are taking 5 seam points instead of 3 seam points. Moving on to evaluation of experiments. Once the experiments are designed, then the experiments are run and conducted, and the results are evaluated. So a reward threshold is defined such that when one point needs to move to a fixed position, then the reward range is 0 to 500 and the reward threshold is 499, which means that if the reward reaches 499, then the result obtained is satisfactory. And likewise, when 2 points are obtained, then the reward range is 0 to 1000 and the reward threshold is 950. So this slide shows the results for the minimal type cloth, and the average step for the preliminary experiments of M11 and M12 are 5 and 27 respectively, and 12 and 103 respectively for M21 and M22, and 118 for M31, because the pre-manipulation experiment is more complex. So this slide shows the movement of the cloth. As you can see, the first image shows a randomly oriented 3x3 cloth, and the agent learns to move the piece of cloth into a fixed position. So 2 points G00 and G01 are moved to fixed position in this case, and M3.1, which is a pre-manipulation example, and here the goal is to flatten the seam points. So as you can see, over a number of steps in this particular example, the seam points fall flatten on the surface before they had some distance in the Z direction. For intermediate type experiments, a similar approach is used, but here 3 points are moved to fixed positions, which means that the reward threshold is 1490 and the range is 0 to 1500. And for the intermediate type cloth, these are the results. So for I3.1, which uses a projection based pre-manipulation approach, the cloth moves to expose the red portion. The red portion here points to the graspable seam, and the goal is to obtain the graspable seam fully on the ground. So as you can see, it does not fully obtain because the projection based approach did not deal well with the overlapping of the cloth. So the red portion is exposed, but there is overlap within the cloth. And for a projection based approach with projection based pre-manipulation with punishments, also this performs better, but not to the extent that we require. So then a slope based approach is finally tested for intermediate cloth, which is shown here, and we can see here that the cloth portion gets flattened. So the red portion is fully exposed and no cloth portion is on top or bottom of it. And since the slope based approach works for an intermediate type experiment, this can be directly translated to a full size cloth, and as is visible here, it will slowly learn to expose the red portion, the flat graspable seam, fully after a number of steps of 489. So it did obtain the flat graspable seam, and there are still a few problems associated with this approach in that the cloth initializations are sometimes too random, which causes self-intersection within the cloth, and this has to do with the way the simulation is defined, such that the grid portions sometimes intersect each other, and so the cloth initializations are random. As part of the future scope, these existing problems are to be resolved, and I'll lay down the proposals for resolution of these problems. One of the proposals include reducing randomness in cloth initializations to make it more realistic, because currently the randomizations are more than necessary. And another approach is to train for larger number of random initializations using vectorized environments. Currently only one seam is selected randomly, but in an ideal pipeline, one of the 4 seam areas should be identified and scored and selected based on which one can get flattened most easily. So this is a pipeline that can be implemented to solve the pre-manipulation problem. And apart from that, for transferring to a real robot, because a camera-based observations are generally used for these systems, an image-based experiment needs to be defined, which means it can be done either by attaching physical markers on the cloth and performing key point identification to identify seam points, or using a deep learning based approach to perform seam identification. And this is just one approach to solving one step of this pipeline. And another approach could be making image crops around the seam area and transforming the cropped image to selected goal position. So a portion around the corner would be cropped and the image would be manipulated to the final state. This would be followed by sim to real transfer, which involves domain randomization of the images and transferring the policy to a real robot. The challenges encountered in this work are, since it is a novel problem, there are no existing experiments for seam flattening. Compatibility of simulation environment, toolkit and reinforcement learning framework was difficult because of finding the right set of tools compatible with each other. Deep reinforcement learning algorithms are highly unreliable, and for some of the experiments the variance obtained was not easily explainable. Moreover, high computational time and resources are required for deep reinforcement learning algorithms because they require huge convergence time. To conclude, as part of this thesis, a methodology is adopted for reinforcement learning problems dealing with fabric manipulation, which start from problem definition, selection of tools, implementation, design of experiments to evaluation of experiments, selection of tools, utilization of a systematic pipeline to obtain a working implementation, design of experiments, execution of experiments and evaluation of experiments, and proposal of a categorization of experiments based on the problem and cloth. So the objectives that were laid out in the beginning have been covered as part of this work. Thank you very much for your attention. That's all from my side.